Good afternoon. It's just turning 1 o'clock. Thanks all for coming. I'll give it another couple of minutes for everyone to filter in, and then we'll get started. Hi.
Hello.
So we're getting up to about 70 people in the room now. I'll give it another couple of minutes because I think we usually end up with over 100. So I'll just, as I say, I'll just give people a couple more minutes to come in before we get going. Okay, well, I'll start. So, hello everyone. Welcome to another Friday lunchtime practical session. Today we are moving on to practical number 3, and I'm going to be doing the last five tasks, I think, from that class. The first part of it you'll have been looking at, which hopefully you did earlier in the week. Looking at sets and operations on sets. Now we're going to look at a few more Python functions, different ways to code up a function and call it, plotting them again, and then going to do some symbolic Python where you can do calculus kind of in a pretty intuitive way. in Python. And then the last thing, if we get onto it, is the advanced topic, which is transformations, affine transformations. I guess, as I've done in the past, I'll see if I can just get a show of hands using your raise hand button of if anyone's managed to have a pop at these problems, have a go at these problems before coming along today. So yeah, if you use the raise hand feature, which is under the reactions button, just raise your hand if you have managed to have a go at any of the practical sheet, because then I can maybe tailor what I do to anything that anyone had difficulty with. Otherwise, I'll just have to go through from beginning to end. I'm not seeing any hands going up yet. So I'll take that to mean that no one's had a go at it yet. So I guess I'll just start at task 7, which is coding up some Python, plotting some trigonometric functions, and then we'll carry on from there. If you have questions, pop them in the chat, or ask your question in the chat, and we can try and answer it, or ask to come off mute, and you can ask it in person. Very happy to have interaction during the class. Okay, so I guess I'll start sharing my screen. Okay, so this is the practical session notes that hopefully you've been able to download from Canvas. We're starting, so already hopefully you've been through this stuff, looking at these sets, looking at intersects and Cartesian products and so on, unions, all the different operations you can do on sets and making subsets, and so on and so forth. And then the practical class kind of changes gear and goes back to looking at some kind of core rudimentary functionality in Python to bring you up to speed on coding in Python. So the first part of this is looking at plotting and using trigonometric functions. And to do this, we'll be importing the NumPy package with our abbreviation NP to make it easier to call. And the task is to generate a trigonometric function for 100 angles between 0 and 4 pi using these functions, and then plot them. So to do this, we're going to use this, you'll probably use this a lot, this Linspace command. And this lets you create an array, a NumPy array, filled with linearly spaced values between two values, a range that you set. So say between here, 0 and 4 pi, we want 100 linearly spaced values. And we'll call that array theta, and that's where we're going to start. And then we're just going to drop that theta into these functions and get the values that we want, an array of values. So the first thing, I'm going to go through this so without all the solutions already written. It can be a bit distracting. So first of all, we're going to import NumPy as NP. I should probably zoom in a bit on this, right? I think there's a lot of people off mute right now. Okay, and then we're going to create this, just as it said in the script. Going to sorry, if I could just ask everyone to mute themselves.
I will mute all, and Ben, if you can unmute yourself after that.
Okay, great. Thanks. Okay, that's better. There we go. So then we'll do this Linspace array that I was talking about. Linspace. We're going between 0 and 4 times, and we're using the NumPy pi, and we want 100 spaces. So that's the syntax for using Linspace. Okay, we can run that, and then we just simply want to, as requested, we want to make get the values for these 100 angles. So we can just do that by writing, say, y sine. What our output array is going to be called, it's going to be called to NumPy sine of theta, and that just creates an array the same shape as theta with those values in it. And we can do that for the other things that we're going to do. So pretty intuitive. So we'll just do this quickly. Okay, and then the next thing we're going to want to do is plot it. But I'm just going to do that and move on to a new cell, so it keeps things tidy. So if we're going to plot it, we want to import matplotlib pyplot as PLT. I'm going to do that. And I'm also going to add, this is a thing that I recommend doing if you're doing lots of plots in Jupyter Notebooks, is just to import this kind of magic line. And this just makes the notebook plot things from matplotlib a bit more reliably. So if you're rerunning a cell after debugging and stuff, it'll dump a new figure into the spot below the cell more. Because sometimes it can get in a bit of a pickle and doesn't always plot again. So doing inline plotting makes sure that it's putting everything out there. It's kind of a belt. We call it belt and braces, just to make sure that you get the plot that you're asking for. Okay, and then what we want to do is plot these things. I think what did it ask is for two curves, different colors and different line styles on the same plot. One for the angles against their sine values and one for the angles against their cosine values. So to do that, we very simply have just having imported matplotlib, we do plot theta against y sine that we calculated up there, and we're going to make that black, and we're going to make this a dotted line. There we go, and we're going to do the same thing, but for the y cos, and we're going to make it a different color. My brain's like a sieve in lockdown. I can't remember 5 seconds what I read 5 seconds ago. We say different line styles, right? So we're going to say we're going to do y cos, and we're going to make this one red, and let's do a dashed line. There we go. So it does what we kind of expect. Matplotlib you'll use it a lot. In its most basic functionality, it's pretty intuitive. So there we go. Simple as that. Task 8, I think, is we're going to be doing more of the same. So we'll keep. We're not. We'll be using these things we've already imported. Where are we? So we're going to be looking at the exponents, and we're going to do a 3-panel plot this time. So we're going to use linear space again. Hang on, no, sorry, I should read this again. It wants us to import this logarithms IPy notebook, which I've already done. And if we have a look here, it wants the job here is to debug this code. We've got these question marks in here. And the task is to do where are we? Log x, log. So we correct the code. Does anyone want to shout out and suggest what I need to put in here? Anyone? Anyone's out there? log base 2?
Yeah. NP log base 2.
Yeah, NP log 2. Yeah, that's how we get. So these are hard coded in, and NP log for log base 10. Anyone take a guess?
Log base 10.
Yeah, with a 10. Yeah. Those are the only, as far as I know, someone can correct me, those are the only 3 logs that are, like, if you want log base 3, you can't just type log 3, and log base 4, you can't just type log 4. You have to do it kind of, using...
You probably have to make a function for exactly.
that. Yeah, you make a function for it. And I'm sure we can all figure out how we might go about doing that. But natural log, log 2 and log 10 are in there as hard-coded. This is something to always keep in the front of your mind. I don't know if this is something any of you run into, but a lot of what I do, I use log 10s a lot more than I use natural logs for various reasons. And a classic bug in code is to, because you're in a hurry, and because when we write logs, we just write log, right? And we write ln for natural log. When you're writing the maths, obviously when you're coding it, that can happen. And so do make sure when you've got stuff giving you unexpected results that you're doing log 10 and you haven't got a natural log in there by accident. That's just a word from the wise. Having had that happen to me too many times. And then we've got the rest of this code here for plotting these 3 plots. So this code, what this does is makes 3 subplots, 1 row and 3 columns, and sets a size, and then we plot each of these logarithms on their own plot, which is this instance of AX0, 1, and 2. Okay, so we're going to have to fix this bit of code. More question marks, which are not good Python. Anyone want to shout what I should be putting in here?
Y2.
Y1.
Y2.
Sorry.
Y2. First one was right. And how about this
Y3.
one? Y3. Nice one. Thank you.
Y3, right.
Great. Okay, and then we'll get the. Oops. There we go. And there we get our three plots, each with their own title. So that's how you do 3 plots in one. Okay. So that was task 8. So now we can jump through to task 9. It's just so now we're getting into more how to write functions, and so as you mentioned, you might want to write a function to do different base logarithms. Lambda functions are one of the ways that you can do functions in Python. So lambda is a protected keyword, so don't use it for other things. But it and if you have lambda, something like f equals lambda. After the lambda and a colon, you'll have your parameters. Sorry, you'll have your parameters, then a colon, then your expression. So we're going to look at using that, and then you can call that function relatively straightforward. I don't use lambda functions very much myself because I don't really think that it adds much to just writing a regular function. If anyone can tell me where they're solve a problem that you can't solve with a regular function, feel free to raise a hand or chuck it in the chat.
They are basically a one-liner function.
Yeah.
And we can do it to, solve mathematical operations. We can use them to perform mathematical operations which do not require a special purpose-built function. We can use lambda there.
Yeah, I see that. I guess it's just I don't find it saves me time messing around with lambda functions. I tend to just write a little function, and then I guess it's just one line, and so aesthetically it's nicer, I guess. But I don't. I guess it's one of those things. I don't really see. I just don't use them that much because they don't any better than doing a function.
Usually in web development where we need to, build the function on a go, we can use lambdas there. This is just one example from my experience.
Yeah.
We do not have to build a purpose-built function. We can just use a lambda function for that particular operation, and then we can just forget about it.
So it's nice and quick, and then it's gone. You don't need to worry about it.
Is there any difference between if we use a for function and a lambda function? Is there any performance-related thing in between two?
Not as far as I know.
No, there is concurrency benefits, functional programming. I think lambda comes from functional programming. So you can run like in parallel on every array element simultaneously.
Okay.
Lambda is faster. It's faster than a general function.
It should be.
That you build it.
Should be.
Yes.
Okay. Cool.
With MapReduce, like in Hadoop and other.
So this is from this comes from MATLAB, is it?
No, it's a general concept that's applied everywhere. So I've put something here about Python and functional programming.
Great.
In the chat. Yes. So even Java included Lambda as well.
Okay. This is me coming from Fortran land, so it's
yes.
Right. Okay. So we're going to make a lambda function to calculate this function minus a plus times x squared. Just go over to my notebook again here. And so we just define the function. This is all just coming out of the PDF. So we have so this is the function f. It's going to be lambda. These are the parameters, and then that's the expression. And then we can put our values in. I think we're going to have a equals 2, and we're going to make x another Linspace array between minus 10 and 10. And then we just I should have run that one. And that one, and then we do, and then we can just get the values, and that's going to be f x and a, and then plotting it. We're going to create this. Plt.figure. These. There we go. So that's a lambda function. The next, I think we're doing another lambda function as the next expression. So this was all kind of demonstrated in the PDF, and then we just have to kind of do it for ourselves as task 9. So it's going to look very similar to what we did before. So I will cut and paste from up here. I'm going to take, there's only an x parameter now though, so we're going to do one over and we've still got it's this minus 10 and 10 is our range for x. So we're just going to leave that as it is because we don't need to redeclare that. And then we can say y is equal to f. And then we can do the same kind of plot that we did before, which I'm just going to cut and paste. There we go. That's hopefully what everyone expected to see for that function. So the next task is to do it using the keywords def and return. So we'll call the function sigmoid def. So that's kind of, this is the way I normally code it myself. I just make a short function. Now on reflection, I think I see the point about it being a lot simpler just to do it on one line. And then and sorry, I've forgotten what we were asked to do here. And then evaluate the function when x equals 0. So the simplest thing we can do is just print and that's the quickest way to get that. And then I think we can also just verify that we can do the same plot as we had before. So we can also just do y equals sigmoid. Okay, so this is going to and then we can plot it. So that's just using again that same linearly spaced array that we had before. And so okay, so it works. We get the same answer when we do it this way. Okay, so that's tasks up to 10. We're going to start task 10 now. This is the last one on functions. Then we're going to move on to using this symbolic Python package. Any questions? Any questions that I haven't covered so far? Okay. So this time we're going to do another function 1 over x, and we're just going to.
Hi Ben.
Hi.
Actually, I just want to ask, like, we are creating here, like, plotting the graphs using the functions, like using the mathematical operations. I just want to know what is the practical implementation. Like, do we need to check the symmetricity of data using this graphs and all?
I think so. I mean, I guess you can think of examples like that. I think the idea here is just to kind of get used to plotting things quickly, to have a quick look at them. So and check how functions behave. So yes, you may want to plot to see whether data is symmetric and things like that. But I think these tasks are really just concerned with kind of going through kind of fairly rudimentary Python tasks, Python operations to kind of grow familiarity with the various functions that are available in Python and how you implement them. Yeah, I mean, I off the top of my head, I can't think of a huge number of practical applications for being able to plot 1 over x. But learning how to go about calculating the values of that function across a range of values and then plotting those up quite quickly and off the top of your head, that's kind of has value because you'll need lots of different things where you want to plot a function or plot some less trivial object that has a numerical output, and you want to have a look at its you want to have a look at what it does across various parameter ranges. Does that make sense? That these are really kind of just worked examples.
Yeah. Thanks a lot for the update.
Okay.
Yeah, thank you.
One more thing, Ben. Just a small question regarding task 6. In, I think it's question number 3, task 6. It's related to the Cartesian product.
Right. Okay.
Yeah. So can you just give a small explanation regarding this Cartesian product and how we can be given two sets?
Sorry.
Like I was having trouble in this.
I'm just trying to find that. Where are we? Here. Okay. So what? Say that again. Sorry.
The third part of task 6.
Yeah. What is the Cartesian product of? Okay. So sorry, and the question is, how do we?
How do we do it programmatically in Python? Like I think this is basically a general question which we are asked to, just calculate.
Yeah.
But, how do we do it in Python? That's
okay. So that's actually there's an example just a bit higher on the page. Using symbolic Python. So you create your sets. Let's see where we got there. I forget what the declaration is to create a set, finite set, right? So you so you create your sets like this, right? And once you've imported symbolic SymPy, and then with those sets as already defined, you then use this asterisk operator, which when you do it on sets, creates your Cartesian, the Cartesian product of the two sets. Okay, and then you can print them out element wise, using a command like this. So this is that's.
Is it just simple set multiplication?
Yeah,
is what I'm getting at.
Yeah.
Okay.
Okay.
Thank you.
Okay. Jumping forwards. Where were we? Task. We're moving on to task 10, weren't we? Okay, so this was just going to be, this is just plotting 1 over x. So this is going to be very similar to what we just did a second ago, but we're going to do it without a function, without a lambda function. We're going to just create an there we go. So we're going to create a Linspace. No, this is going to be this one's arranged, isn't it? Yes. So we want to start off. We want to make an array which goes from 10 to 1000, and we'll give it spacings of 1. So this is the A range function. By a range, and we say from 10 to 1000, and we want to give it space 1 in spacings of 1. Okay, and we're going to make x equals that, and then y is just going to be 1 over x, and then we're going to plot that. So this is Plt Plot. We've already got all this stuff loaded. We've only got one axis. And we're going to set label. There we go. Next. 1 over x. Okay, so for quite a simple one parameter function, you can just do it. It
could be x dot set y label.
Yes. Well, yes, thank you. There we go. Okay, now that's going to work. Thanks. Didn't have an embarrassing error come out. Nope, we still get an embarrassing error come out. MPy a range. Oh, sorry. I have a problem with brackets. I always default to a square bracket, and then obviously when you're calling the function, you want round brackets. There we go. We actually, could have used the same very simple way of coding it for the sigmoid function as well, since it only has a single parameter. But that's how you do it without any kind of without a function. The next item, as we go forwards, the last two tasks, 11 and 12, are using SymPy, and we're going to be finding limits of a function with this. So I guess we'll just get started. And yeah, before because we're changing tax, does anyone have any more questions? I've seen there's a few questions about what's plt.gca. This kind of creates your plot, if you like. Plt.plot creates your plot object, and then when you do the GCA method on it, it kind of sets up your axes and everything like that, based on no input if you leave this blank, or you can obviously specify things that themes or things like that you want for your axes. But this, if you don't already have an axis, it creates one. Otherwise, it puts this onto one that exists, and then you can plot onto it. Does that make sense? Get current axes. Right. So we're going to import from SymPy. And we're importing, we're going to be using limit. We have to declare a symbol, so we're going to be using symbol. And we're going to make x right. And then this is the limit we're going to set up, 1 over x for x to infinity. That's going to be equal to limit, capital L limit. Oh, I've done something silly here. I'm just going to cut that cell out. Sorry. There we go.
Can you please zoom out your screen?
Zoom out. Like that.
Thank you.
Everyone can still read it. So let's take a moment to look at that. What we've done is we've set up x as a symbol for symbolic pi, and then we've used it in this limit expression, and then and that's what we get echoed when we invoke it on its own. But if we want to actually know what the value of this is, then we use the do it method, which is this. And we get, as we'd hope, we get 0. So those are that's the kind of the most basic way of putting it in there. But you can also set a direction. So let's say we want its limit to 0. Okay, and we want to do it in the negative direction. Okay, so that's how we do that. So you're just going to put this into this cell. There we go. And then we can look. What do anyone want to take a punt at what we're going to get when we run this? See if you understand what this limit thing's doing. This is 1 over x.
It will only calculate in the negative direction.
Yeah.
From 0 to negative.
Negative.
I think infinity, is it?
Mm-hmm. Yeah, it's going to give us negative infinity, exactly. And similarly, if we put a plus in there, it's going to give us positive infinity. Okay.
What regarding the symbol? Why have you declared it as symbol X? Like, is it to initiate the symbol function or the class symbol?
Yeah. It's so yeah, we create this instead of it being like a variable, is the way I understand it. So instead of it being something which we will then have to assign numeric values to in order for it to calculate the limits, if you see what I mean. If we put an array of values into here, it's not gonna work with it. So this is initiates X as a symbol in symbolic pi. I think, if that makes sense.
Thank you.
Yeah. So the next things we're going to do in the final task is look at differentiation with symbolic pi. So we're going to create a function where we have X as a symbol in the function, and then we can then get a derivative of that function, and we can evaluate that derivative with the do it method. Okay. So we've already got symbol imported, so I'll import from SymPy. We're going to import import derivative. Okay. And we've already got X set up as a part of the symbol class. So the next thing we want to do is set up this function, which was f equals 100. Where are we? 100 times x squared plus 4x plus 9.
It's 100 times x squared, then remove plus sign.
Thank you. Oops, there we go. Yeah. Thank you. When I code, I frequently have code that's riddled with typos. So I appreciate having extra eyes to look at it. So then we're going to create this derivative, f with respect to x. Okay. and that's what that looks like. So to evaluate it, it's the same as we had with the limits. We want to do we want to use the do it method. So the differential is going to be that derivative dot do it. Sorry, derivative. There we go. Actually, if we just do it like this, we get a nicer, looks a bit prettier. Okay. And then if we want to evaluate it, we use a substitute method in there, which is what it asks us to do in the next task. So we've got that derivative. We use the subs, and we put in the value in there, and we'll get our value out. So we do df subs curly brackets. We're going to substitute 2 in for x. Ah, 1 in for x. There we go. Okay, is everyone happy with that?
Yes.
Great. Just going to put some more cells in. So the last is more of the same. We've got this function, and we're first of all going to be your job is to get the derivative of x on paper, and then find it using SymPy, and evaluate it at x equals 2.
3x squared plus 4x plus 1 over x.
Yeah. So we can do this. We've got everything we need imported. We've got x already exists as a symbol. So we're going to say y equals x cubed plus 2x squared plus, and the warning it gave us in the script was that we have to use SymPy, not NumPy, lun. Why not? What is that? I guess I need just to import it as just import the whole thing, don't I? Import SymPy. There we go. So then we want to get a look at that. So we're going to say df equals derivative. This is just as we did before, right? And we want y with respect to x.
Do it.
Yeah, do it. Thank you. And we'll have a look at it. There we go. And it is exactly as someone called out and helped me out. That's what we expected to get, and then we can then evaluate it using the subs. Yeah. What was it we were substituting in for it? I can't. Do I need
X
to
equal to 2.
X equals to 2. Thank you.
Yes.
Excellent. X equals 2. Great. We run it. 41/2. So, and that brings us to the end of the set tasks in this left. Are there any questions on this?
Why are we using SymPy instead of NumPy? I'm pretty sure there are different functions for differentiation and integration, as well as logarithmic functions in NumPy. And NumPy is, from what I know, is faster in processing mathematical operations.
Yeah, because a lot of NumPy is in C, isn't it, at its base level? So it tends to be quite quick. I'll be honest. I don't know what the advantage of using SymPy for this is, because I don't do a lot of symbolic, algebra or calculus in Python myself. So I've not kind of run into the kind of the nitty gritty of why you'd want to use SymPy over NumPy. I've only done this kind of thing in SymPy, so I can't tell you whether it's clunkier or more annoying in NumPy. I mean, most of the stuff that I know NumPy is quicker for is when you're doing kind of big arrays and things, right? I mean, it's still not as quick as doing it in a proper language, but
for example, in algorithmic trading, in those applications. From what I've seen in general examples, mostly NumPy is used, and there's a lot of data there to analyze and to plot as well.
Yeah.
So just a general question regarding that: why use a library that is new as compared to NumPy, which is a very old library, and it's the fastest one? I think it's the fastest one.
Symbolic math, SymPy is for symbolic math. I've put on the chat the link to where your question is answered. So it's mainly for using symbols like X and Y when you don't have matrices of numeric values only in NumPy. When you have symbols, it's good to use SymPy, and it's good for students to learn and to verify their algebra answers.
Okay, thank you.
Sorry, I misunderstood the question. I thought that you were saying that there was the capability to do symbolic maths in NumPy, which I wasn't aware of. But so yes, we're using SymPy because this is symbolic. This is symbolic maths, and that's why, for example, here we're using SymPy Learn because we're handing it a symbol object rather than numeric value. Okay. Yes, but as I said, it's not something I do a lot of in my real life of doing symbolic work in Python.
Could you scroll to the top, please?
Yeah. So the last bit of this practical sheet, which I'm not sure we've necessarily got time to dive into very thoroughly, was an item here. Where are we? Looking at affine transformations. Did anyone have a look at this? There's a kind of a useful page linked, which looks at how to do this, and it's got some example codes and things like that. I'm kind of on the fence. Would anyone like to look at this if we have a couple of minutes? Someone's asked to explain task 8 again. Okay, I'll go back to that. Do follow through on this this link that's at the bottom of the practical. As I say, it's got example code that you can cut and paste and play around with and see how you can do kind of simple rotational or scaling transformations. It's not a bad idea to have a look at it. But task 8, which was this is the logarithms. Okay, so this was in practical 3 logarithms. This is this notebook. So explain task 8 again. So I guess I can go back in task 8 we had this. We were asked in the script to download this. Find it. This logarithms, practical 3 logarithms IPy notebook from Canvas, right? And we have log x, log to the base 2x, and log to the base 10. And it's done with these. It's one of these. We've had this in another class, right, where we download a notebook and it has question marks in place of things, and you have to pop in what you want there. So it's really just a case of noticing that there are 3 kind of log functions built into NumPy, and that's natural log, which is log, log base 2, which is log 2, and log base 10, which is log 10. Is that the kind of explanation you're looking for? So for these bits here, if we're doing log base 2, we do NumPy log 2 x, right? And we do NumPy log 10x for base 10. Does that make sense, Hardik? Okay, and then this is the bit where we replace these question marks as well. What am I doing? Well, Y2. Someone helped me out with this when we did it before, didn't they? They shouted out the answers, and that's why I didn't get it wrong. There we go. And then we run it, and we get these 3 plots. Does that make sense on task 8? Okay, great. Any more questions? Got 200 of you now. The last task, was that the, do you mean the affine transformations bit, or the last bit of symbolic pi? Okay, yeah. I've got this. We're kind of out of time, but I can. I think. Manal, sorry, just to ask a question. The solutions are going to get posted up soon, right? After everyone's had a go at having them, I think this is what's happened in the previous weeks. And the affine transformation code is in the solutions, but it needs to be fixed. So I will pop up here. Okay, I'll pop up the code that I've got that works. So on this page that you go to, it starts the example it's taking is drawing these diamond shapes, which where's the first version of it? Which in its first instance is kind of centered around 0, with point A at 1, point B at 1. This is at 0, 1, and then this is at 1, 0, and then this is at 0, minus 1, and minus 1, 0.
Minus 1, 0.
Yeah. So this is the points A, B, C, D that it sets up. Okay. And then it creates a matrix of those based on the vectors for those points. Okay. And that's kind of the basis which you then work forwards from for doing some escape. And so this is really, you know, the if we look at this notebook, the PDF of what it asks you to do is do some experiments using your own images as well. But cut and pasting the code or a version of the code into a notebook. So you start off with these points. We make that matrix, and then we make a scaling transformation matrix, which I've got set here to 1, so we can see what it looks like initially. So we do that, and we get this this funky little diamond, right, which is centered at 0, and then we can look at, say, doubling its length, and we end up with this elongated diamond. We can double its height as well. You get the idea, right? So that's the scaling.
A question regarding this. Can we use this on the image that we used in the last practical using for SVD? Could we use this on the cat image and then try to rotate it as well, like something like that?
You can, but because what you're doing is you're taking a dot product, you'll need your transform matrix to in some sense match up to it, right? I think. Or am I wrong? No, I'm not wrong. Yeah, yes. This is just you can just use this on there. Yeah.
We could extract the points of that cat image and then we transform the matrix and then perform the affine transformation.
Yeah. So you extract them and create. Which, I mean, the code's already in there to do that, right? Because you do the to extract the points because of doing the SVD on it. So yeah, you could take that notebook that you have from that and just drop another cell in and start playing with this. But just thinking about for plotting it. To have a look at what you're doing, you'll want to be you'll want to be using the image plotting stuff rather than this. Obviously, the code is for a scatter plot, and that won't work. Okay, does that make sense?
Can we use matplotlib for that as well?
This is why I don't do enough with images at the moment. I'll have to grab the. I got the notebook handy. I can't remember if the image plotting thing it comes out of matplotlib. I don't think it does. I think it's if you have another package for plotting the image. So I think you'll need to do a bit of messing about to get it to work, but it shouldn't be too bad. I think. But I having not done it, I can't tell you off the top of my head how well it.
Sure, I'll figure it out. No problem.
Yeah. I think it's it'll just be a bit of hacking to make it work, but it's a good thing to try and do.
Yeah, the rest of the link says actually that Pilo is the image programming package in Python. So usually Matplot is for plots only.
Cool. Yeah.
All right. Thank you.
Can read from a plot and image, yes.
Yeah, imread and but PLT that's what matplotlib was imported as, right? So yeah. So you can do an image with it, but you use imread and imshow. That's what it is. Okay, so we're over time now. So the last question about getting solutions. Yes, the solutions will be posted. Just stop sharing now.
Ben, can you share the link of the page you are reading?
It's on the. I'll pop it in the chat. Yeah, but it's here. It's on the PDF of the practical class. But there's the link.
Yeah, thank you.
But if that disappears, it's there in the PDF. So I forget what the delay is for the solutions going up on Canvas, but it's after you've had a healthy delay to have a go at doing them yourselves. But they will appear again. Okay, so thanks everyone. It's sunny where I am. I don't know if it's sunny where you all are. I hope so. Someone mentioned it in the chat earlier. So do get some fresh air in amongst the lockdown if you're in Hertfordshire. Have a good weekend, everyone.